Thermodynamics, today's topic, and obviously very important topic of this unit, heat and thermodynamics. This chapter is very important regarding competitions like NEET or JEE, mains or advanced. Every year, at least one question is asked in all these exams from this particular chapter. It's very interesting. Definitely, you all enjoy it. So, see the term thermodynamics. Let us divide this chapter in two parts: thermo as well as dynamics. The term thermo, as we know, it means heat. Thermo means heat. Dynamics is the study of motion. So, obviously, you can check. See, surprisingly, there is no direct relation between these two terms, heat and motion. Right? But here in this chapter, we will understand the correlation, interrelation between these two things. Or better to say, thermal energy, a relation between thermal energy and mechanical energy. Mechanical energy. Right? Means we will understand the relation between these two energies, how can we transfer one form of energy into another, and vice versa. This chapter deals with that, and this chapter, according to that, in this process, will deal with some basic rules of nature called laws of thermodynamics. Okay, so we understand basically the chapter deals with the relation between or interrelation between thermal energy and mechanical energy, how one can convert thermal energy to produce or convert thermal energy into mechanical energy, or how can we use this energy to produce mechanical energy, or we can say what, to produce mechanical work. Yes. And the device, the instrument that is used for this purpose is called an engine. Engine, basically heat engine. Heat engine is the device which is used to convert thermal energy into mechanical energy, or to get mechanical work by using thermal energy. This is what the domain of this particular chapter. But the phenomena are obviously not so simple and need some rules, some restrictions. So we have to go through step by step. Dealing in that, the first thing which we must discuss about, what is a thermodynamic system? Thermodynamic system. A thermodynamic system is, obviously any system is about some molecules, some atoms taken together, matter in any form. For example, say gas. If you contain some gas in a container, right? If you take some gas in a container with a piston, some gas is there. This is a system of gas molecules, and definitely it is confined within the boundaries. These are the walls of the container, here the piston. So gas taken over here is confined from all sides, and also it's separated from, taken separately from the surroundings. So this one, the gas inside the piston, inside the cylinder, is known as a thermodynamic system, and other things outside, means the air, you can see. These are our surroundings. There are two things: system and surroundings. System as well as surroundings. Depending on this basis. So, simple classification of the system is, first type of system that we know is an open system. Open thermodynamic system. An open system is what? Open system, to understand open system, let us take some water in a container. Let us take some water in a container, right? And keep it somewhere in the room at room temperature, and leave it for some time. You will notice that after some time, the level of the water has come down. That simply means some water has been evaporated. Some water has evaporated. That means the molecules or the matter kept in the container, the matter of the system is transferred to the surroundings. So here, what is being transferred? Matter is transferred. Not only matter even, and since evaporation is a slow process, definitely, and here you see the temperature. As you know, in any case, you all know in summer seasons, you all know the beaches, earthen beaches, which are used in houses, in the rural areas especially, to keep the water, drinking water especially cold. And why? How does it make it keep it cool? It keep it cool because of a process called evaporation from the surface of the pitcher. Right? There is capillaries over there, and through this the water comes to the surface. From there it gets evaporated. We all have learned this in the previous lessons. And during evaporation, it needs some heat. The latent heat of vaporization is taken from the water itself, and that's why it gets cooled or its temperature goes down. Temperature goes down means definitely its internal energy of the molecules of the liquid has decreased. So what the concept is? That simply means in that system, what we notice that matter as well as energy. Or energy in the form of heat, yes, is transferred to the surroundings or is exchanged with the surroundings. Either may be given to the surrounding, may be taken to the surrounding. Such systems are called open system. Now see, second type of system are closed system. To understand the closed system, we can understand this system also. The gas kept in a container, the piston, right? This is a closed system because all the boundaries, the gas is enclosed, kept in an enclosed system which is closed from all the sides. From this side, here is a piston which is movable, here are the rigid walls. So this system is a closed system. Now in this case, what is possible? In this system, definitely no gas is allowed to escape out to its surrounding. Means you can't, there you will not get any gas molecule outside the system. That means there is no exchange of matter taking place. No exchange of matter takes place. Right. But yes, one thing is there. If this gas temperature of surrounding is less than that of the system, then what will notice? Then gradually you will notice some cooling in the system. The temperature will go down. That means the system will reject some heat to the surroundings. That means even when there is no exchange of matter with the surrounding, there is an exchange of heat allowed from system and the surroundings. So this kind of system are closed system. So in closed system, the basic difference between open and closed system: in open system, matter as well as energy is exchanged with surroundings, whereas in the open closed systems, only energy or heat is allowed to exchange, but no matter is exchanged. This is the second one, and third one is an isolated system. Isolated system. Let us see, to get an isolated system, if what we do, we can make some basic changes in this system. If I cover the whole container, even the piston, like this, by an insulating material. This is what an insulating material. You may make a blanket, woolen blanket, etc. So this is what insulating. That means this system is Now completely insulated, it is covered by insulator so that no heat is allowed to either enter into the system nor it is allowed to leave the system to the and go to the surroundings. That simply means in that case the exchange of matter, neither we can say neither an exchange of matter nor an exchange of heat is taking place. So basically we have classified the system in three types: open system, closed system and isolated system. Okay, open system, closed system and isolated system. And to define a particular system, the parameters of a system, we have to define system, how to define or classify or differentiate one system from the other, right? By the help of its some variables, the parameters which are called thermodynamic variables. Thermodynamic variables. What are these variables especially in the case of the gaseous system, which is made of gas molecules? There are three thermodynamic variables used, and one is the pressure. Right? So pressure, as you know, pressure is what? Pressure is the force. Pressure of the gas is the force exerted by the molecules of the gas on walls of the container. The pressure is obtained by dividing the net force exerted by all the molecules on the walls of the container divided by area of this particular surface. So pressure exerted by the gas on a particular surface is the force exerted by its molecules divided by area. And definitely its unit is Newton per meter square. Okay, or even in Pascal it is used. Second one, the second variable is its volume. Volume, you know well, volume is the space occupied, right? Volume having unit, SI unit, cubic meter, and the third thing which is used to define a thermodynamic system is the most important is temperature. Here the SI unit of temperature is Kelvin. We all know temperature. Temperature is nothing but the degree of hotness or coolness of the system. How hot or cold the particular system is. So there are three thermodynamic variables, and every thermodynamic system has a specific value of these three variables: pressure, volume and temperature. And a specific value of these variables makes the state of a system. If they ask you what is the state of a system, thermodynamic state of a thermodynamic system means the value of these variables: pressure, volume as well as temperature. This is what the system is. And in this system, so they are the case. Now let us have one more thing in discussion of this thermodynamics. So thermodynamics, as I told you, thermodynamics is a subject, as a branch of science which deals between the relation. It is the relation between heat and mechanical work or mechanical energy. Okay, let us deal with the law. First law. So, first law is there is a law. There are certain laws out there. First law we call first law here, that is first law of thermodynamics. Yes. First law of thermodynamics. Yes. This law says what? This law says that if we have a system, see the statement. If we have a system, thermodynamic system, that means suppose we have taken certain amount of gas in a container, say there are n moles of the gas, n moles of a gas, n moles of a gas is taken. Right. It may be monatomic, it may be diatomic, polyatomic, whatever. So there are n moles of a gas taken in a container, certain amount of gas is taken. Right. And here is the piston. Piston is movable, and not only movable, it it should be light in weight as well as it should be smooth, means frictionless. There should not be any friction inside the walls, right? Suppose for example these are conducting walls, and if you supply heat to the system, if a heat is supplied, suppose dq amount of heat is supplied to the system, what can happen? If dq amount of heat is supplied to the system, definitely what is happening? There are two possible things which can happen. You will notice that the gas expands. You will notice that the gas starts expanding. Yes, the gas is expanding. So gas expands. Piston moves from position A to position B, and say it goes up through a small resistance X. And since here we are just raising the temperature, giving it the heat, we can notice that the gas is expanding. And not only that, if we insert a thermometer inside, we will also notice that the reading of the thermometer is increasing gradually. That means there are two things. One, due to the supply of heat, by absorbing heat, the system do what? System reacts by absorbing heat. Your system reacts in two ways. One, it gets heated, or we can notice that its temperature is rising up. In the previous chapter of KTG, you have learned that temperature is directly associated with internal energy, or basically the internal kinetic energy of the molecules. So we can say what? With rising temperature, the internal kinetic energy has increased, or we can say, we will notice, in other words, we can say there is a positive change in the internal energy. That is what we represent by the term D. So D represents a positive change in the internal energy, means when temperature of the gas is increasing. Now, that is not enough. One more thing we have noticed, that the piston has moved from position A to B. It has gone up through a distance x, and it has gone up. That means the gas has expanded. Since the gas has expanded, and gas has expanded, definitely there is a work done by the gas. Piston has not moved by itself. The molecules is striking more vigorously, forcing the piston to move up from A to B, and that means we can say there is a positive work done by the gas. Okay, so there are things. This is a very simple statement, but we will discuss everything in detail, in all the terms in details. There are n number of thermodynamic processes, in which these operations can be performed. So the basic law is what? dq, the amount of heat absorbed. dq is what? Amount of heat absorbed by a system. Absorbed by any system is used up by the gas in two ways. One, by increasing internal energy. So this is what? An increase in internal energy. Increasing internal energy. As well as by performing a mechanical work. Some mechanical work. So there are two ways we can see it clearly, that the amount of heat absorbed by a thermodynamic system is used in two ways. One, by increasing, it reflects to us in two ways. In that one, in the term of rise of temperature, means T is increasing, or we will have delta T or dt. So we can say it is a rising internal energy or increasing internal energy, means the particles, say the molecules or the atoms, these have become more vigorous, more energetic, and they are right now, they are more frequently colliding with the walls of the container as well as the piston. So definitely there is, we can say there is a, so the rising temperature even notices that there is a rise in internal energy. And not only that, if you see something is, the piston is going up, moving up, means the gas expanding, we can say there is a mechanical work being done by the gas itself. So this is what the statement of the first law. So in other words, we can write down that du is, or increase in internal energy, increase in internal energy is what? dq minus dw. So that means if the amount of heat given to system is dq and it performs some mechanical work dw, then increase in internal energy will be dq. We will try to understand all these terminologies one by one, right? And for that, we have to understand these topics one by one, the terminologies one by one, and see how the things come. Thermodynamic process. Let's see. Thermodynamic process. What is the meaning? There are n number of ways, or there are so many ways in which we can change in the thermodynamic state of a system. Right? That operation, that phenomena is called thermodynamic process. There are so many types of processes and we will discuss them one by one. So these are n number of ways in which we can change the thermodynamic state, or we can, that is what we can say, a system is taken from one thermodynamic state to another thermodynamic state. Okay, let us see the basic things first. Internal energy, and we have just seen a new term over here. Since we have discussed this in detail in KTG, internal energy of a system, internal energy of a gas, or internal energy of a gaseous system is what exactly is the sum total of two energies. That means internal potential energy as well as internal kinetic energy. Internal kinetic energy, right? So internal energy is nothing but the sum total of two energies: internal potential energy or potential energy of the system of the particles, means the molecules or the atoms, and second, the internal kinetic energy, the energy that is there by virtue of motion of the particles of the gas. Internal energy, you all know, you have learned in detail about the potential energy. Potential energy, in fact, is the energy which is there by virtue of configuration or position. So by configuration process phenomena, it is exactly clear that the potential energy of a system is there. It exists only when the particles or the particles of the system, they have some interactions. It means if there is an inter-particle interactions, the system of such particles definitely have some internal potential energy. And if you want to change the configuration, right? We have learned in electrostatics too that if you have a system of some charged particles, right? Since they interact with each other, they either attract or they repel. So this is the scenario when this case is there. Such cases there is interaction, and if you want to change the configuration of the system, definitely some additional external interference is required, external input is required, external force is required, or there must be some work done on the system, or either positive or negative, to change the potential energy, to change the configuration, right? So this is what the internal potential energy. But in this chapter, especially in ideal gases, we have used some assumptions called postulates, right? In postulates of KTG, we have considered that there is no interaction between the molecules, neither between the molecules, nor there is any impact of the forces, effects like gravity or so. Since there is no interaction, neither attraction nor repulsion, right? So as you see, it is clearly visible in the case of solids, right? And even clearly visible in the liquids. When we see, it is really impossible to compress a liquid like water. Water is almost incompressible. Why incompressible? Because it is not easy to deform the configuration of the particles. But in gas, since you know well, gas molecules are widely separated, having lot of intermolecular space and very weak intermolecular force, right? So we can say what the interaction is not there. Interaction is there, but only at the time of collisions. They are colliding with each other, and just by colliding, they share their energies with each other. So we can neglect this part. So we can say what internal energy U of a system is nothing but the sum of kinetic energy of its particles. Right? Law of equipartition, if you remember, law of equipartition of energy states what? That kinetic energy of a molecule, of a single molecule, right, per degree of freedom. Kinetic energy of a molecule, of a gas, right, okay, per degree of freedom is 1 by 2 K into T. Is given by T, K, T. K is a constant, but Boltzmann's constant, right? K is the kinetic energy of that particular molecule, and this kinetic energy of the molecule is half K into T, where K stands as for Boltzmann constant. T is its absolute temperature. T stands for its absolute temperature. T stands for its absolute temperature. T stands for its absolute temperature. K stands for a constant called Boltzmann's constant. Boltzmann's constant. Right. This is what the kinetic energy of a single molecule of a gas per degree of freedom, right? And if F be the, if N be the number of moles of the gas, N be the number of moles, then therefore number of molecules N will be, you all know, in 1 mole there are Na, so a small n into Na. This is the total number of, if the number of moles of the gas, then number of molecules in the gas. This is what the number of molecules of the gas. Number of molecules present in n moles of the gas. So for the total gas of n moles, we can write down this expression as K is equals to 1 by 2, right, n small n into Na into K into T. Na into K, Avogadro's number, where Na stands for Avogadro's number, you know, Avogadro's number, right, and Na into K, Avogadro's number multiplied by Boltzmann constant is another constant. We call it universal gas constant, right? So this is again kinetic energy of n moles of a gas per degree of freedom, and if F be the degree of freedom of the gas molecules, degree of freedom, yes, degree of freedom, and we know well degree of freedom, we know for monoatomic gases, right? Monoatomic gases, F is equals to 3, and for diatomic, F is equals to 5, or even a high temperature, maybe 6. So there are 5, 3, and 5, right? So these are the F. So for a monoatomic gas, we can say kinetic energy Ke of all the molecules at a temperature T and an absolute temperature T is given by F by 2 nRT. This is what we can say internal energy of the gas at a temperature T. If I differentiate both sides, yes, dk will be F by 2 nR dt. F by 2 nR dt, or we can say n into F by 2R dt. The term F by 2R is used as Cv, called molar specific heat at constant volume. Okay, so we have just finished that dk. We can say the change in kinetic energy of the molecules of the gas is given as n Cv dt. Here Cv is a term. Cv is an important term. Cv is called molar specific heat at constant volume, right? Decay. And we have just seen that the internal energy of a gaseous system is what? Nothing but its kinetic energy. Hence, any change in internal energy also means change in its kinetic energy. So we can now get a formula for du is equals to NCV dt. Okay, which is what, and this is you have to keep in mind in certain questions they ask you this case, and du is equals to NCV dt, right? And CV is what? F by 2R dt, right? F by 2R CV. Achha, one more thing they ask you, see, Cp minus Cv is equals to R. Cp is another molar specific heat, but this time it is at constant pressure. So Cp minus Cv is R. We have learned these relations earlier. So Cp minus Cv is R, and we know Cp upon Cv is gamma, right? Poisson's ratio or thermodynamic constant. So Cp upon Cv is gamma, and Cp minus Cv is equals to R. So we have Cp upon Cv minus 1 is equals to gamma minus 1. This will be Cp minus Cv upon Cv is equals to gamma minus 1. Cp minus Cv is R, since R upon gamma minus 1 is equals to Cv. We can read out this expression as N in place of Cv, right? R by gamma minus 1 into dt. Now say, what is the benefit of this? Here we have seen R is there, and nR dt upon gamma minus 1. N is number of moles of the gas, R is the universal gas constant, and dt definitely change in temperature. So if the system is taken from temperature T1 to T2, that means that the state of the system is changed. Means the temperature is raised from T1 to T2. We can get the change in internal energy just by increasing dt, because except dt, temperature, all other are constants, so they have been taken out of the integration. So if the system is taken from initial temperature T1 to T2, which internal energy that varies from U1 to U2, we can get an expression for change in internal energy, or we can write down U2 minus U1 is nR upon gamma minus 1 into dt, that is T2 minus T1. Okay, so we can write down this as nR T2 minus nR T1 upon gamma minus 1, right? And you all have learned the cases of ideal gas equation. We know from ideal gas equation, ideal gas equation tells us that PV is equals to nRT. PV is equals to nRT, and here in this case, if pressure or volume are there, say at temperature T1 pressure is P1, at temperature T2 pressure becomes P2 and volume becomes V2. So here I can write down P1 V1 is equals to nRT1. Similarly, I can write down P2 V2 is equals to nRT2. So nRT2 is P2 V2 and nRT1 is P1 V1. We can write down P2 V2 minus P1 V1 upon gamma minus 1. Please keep in mind these simple expressions so that you can use them directly in the given numericals, and that will save your time and energy both. Okay, this is what about internal energy. We have just discussed change in internal energy, right? So this is the case in case of internal energy. Now come back to the next term, dW, or we can say a small work is being done. dW, work. W is the work done. We know well there are two kinds of work done. We have learned in class 11 in the initial chapters of work energy power that there is a system, then there are two kinds of work done positive. Either a positive work done, right? Either a positive work done or a negative work done, right? Negative work done by the system, right? If these are the work done, possible work done by system. When does the system does work, right? Let us try to understand this. Let us try to understand. Say we have taken again some gas in a container. Right. We have taken some gas in a container and, right? Then here you see, if the gas is taken in a container, piston was at position 1 due to any of the process, right? I supply heat, okay? Anyhow, if the by raising the temperature directly, we can see what if the piston goes up, displaces up, right? If the piston is displaced up slowly, right? What is the case? In that case, you can see your gas expanding. That means whatever if the pressure of the gas is P, and say it may be constant, it may not be constant, right? That's a different issue. We'll discuss it later on. So let us say at that instant that the pressure is P and if it is constant, and at this constant pressure, you can see the gas is expanding, going piston is moving from position 1 to position 2. And if area of cross section of the piston is, area of the cross section of the piston is suppose A. Area of the cross section of the piston is suppose A. Then, right, then force exerted by the gas on piston will be, how much force will be exerted by the gas on the piston? Yes, definitely forces pressure into A, P into A. And if the piston get displaced, if the piston is displaced, piston displaces, we can see that in that case piston is getting displaced to a distance say x, right? A small distance x or dx, just taken through a small distance dx. Then work done by the force exerted by the colliding molecules of the gas on the piston. Work done by the force will be, obviously work done will be force into displacement, that will be P into A into dx, right? Here we can see A dx, this term A dx. A dx is what exactly? A dx is this extra volume. A dx is the extra volume, or we can say the work done by the force or by the gas, or work done by the force exerted the molecules, or simply work done by the gas in this process is P into B, right? That is simple and obviously very easy to understand. In that case, this term pressure multiplied by change in volume is the work done by the gas. If the gas is doing some work, right, pressure is there. Pressure is not always constant. That means if you want to integrate it, right, it's not necessary that you have to keep P always out of the integration. And if P depends on V, if P, in some cases, P may be given as a function of V. Yes, means there is a variable P that is increasing with V. For example, in case of isothermal process in Boyle's law, if you remember, what we know, pressure of the gas is inversely proportional to V. That means this law states for a given amount of gas at a constant temperature T, the pressure of the gas is inversely proportional to V. That means P is an inverse function of V, right? And P is a function, P is not a constant. Since V is increasing, definitely P is decreasing, definitely P and V are interconnected, are interdependent, hence P cannot be taken as a constant in such processes, right? So we have to be careful about that. P, if it is a function of V, any kind of function, then we can write down it is V, FV, dV, and we have to integrate from the range in the range V1 to V2, and we can get W is equals to this. So the work done by the gas is given like this: Fe dV V1 to V2. For Fe is what? P. P is a function. P pressure is expressed as a function of volume. Okay. In case of this is how we calculate the work done by the gas. Now see something else. Okay. Say let us have some gas in a container with a piston over here. Okay. Right. And on this piston, if I have placed a block, mass of the piston is neglected, okay, and mass of the block is supposed M, right, and here is some gas in the system, in the container, right. We notice that the piston is in equilibrium. The piston along with the block is stationary, is in equilibrium. That simply means the force exerted or the force on the piston, right, net force is 0 on the system, on the piston along with the block in the system. This is the force. Force is what? Mg, the weight, as well as there is a force exerted. There is a force exerted over here, right? And this force is there. Now, if I keep another block, one more block of equal mass, say M. So there are two blocks now, okay? Each of mass M. And you notice that, what you notice? You notice that the piston doesn't remain equilibrium in position 1. Rather than it comes down to some other new position, it attains a new position here at 2, and yes, definitely again the whole system attains what? The whole system attains an equilibrium. The whole system attains an equilibrium, right? Again, that simply means what? You see, it has come down since we have increased the force. Definitely, and again here is a piston over here. So new pressure is different. Pressure is now P2. Here pressure was P1. Why? Because if this is not more, how can we balance the extra load? That means this P2 is twice of mg upon m. Whereas P1 was mg upon m, right? That means pressure has get double. Or say P1 as P, then this will be 2P. Yes, the pressure has increased, but in that same, we can see what? The piston has come down to position 2. That means, suppose if this displacement is dx, right? Yes, there is a compression in the gas. The volume left is this one now, not this one. So volume has reduced. Okay, and in that case, what we can see, dV or dV minus dV is there. Decrease in volume means compression in the gas, and dV is what? AdX. Change in volume or decrease in volume is AdX, right? And definitely here, if at that case, we can find out P as a function of V, and since temperature has been kept constant, right, means that the pot, whatever heat is allowed to escape, coming out, let it go, let it enter, whatever, right, the walls are made up of ideal conducting walls, means heat is allowed to either escape out or even enter, just to keep the temperature constant. So this is performed, is done slowly, in a slow process, slowly done when temperature is kept constant, right. We can say this case is obeying Boyle's law, or we can, if I want to calculate W in this case. Is gas doing some work? Definitely no. Gas is not doing some work because a gas cannot compress by itself. To compress the gas, there is an external effort to be made, and we have made this external effort by doubling the load. Initially, the load was mg, now the load is twice mg, right? And the system, the piston with the blocks attain equilibrium, right? In new position 2. That simply means what? The gas has compressed, the volume has decreased, and in that case, W, the work done, as you know, is P dV. dV is what? Negative. Since dV is negative, yes, this work done will be negative. So compression, very simple things to understand. Compression indicates what? Compression indicates negative work done by the gas. Negative work done by the gas. Wherever, in any calculation, in any numerical, if you get the work done, suppose you are calculating and at the end, you are getting a negative amount of work done by the gas, right? This is what means your gas is compressing or negative work done by the gas. In case of compression, it is said that work done by the gas is negative. Similarly, in expansion, it's just opposite of that. An expansion means positive work done by the gas. Positive work done by the gas. That means there are two kinds of voltages. Either work done by the gas, or work done on the gas, right? Negative of the work done. Of work done, let us have a relation between these two. Work done on the gas. In questions they ask you, just by changing the terminologies, a little bit change in the terminology, they may confuse you in their questions by asking like that. Work done on the gas. Dear, work done on the gas is nothing but the positive value of work done on the gas is nothing but negative value of the work done by the gas. Right? Similarly, that means in that particular example given, if the gas is undergoing compression, volume is getting reduced, definitely we can see work done by the gas is negative and is what? Minus PdV. Therefore, work done on the gas, the work done on the gas is negative of the negative. That means it will be positive. Right? So this is what the situation is. We can understand it clearly. Work done by the gas or work done on the gas. When work is done on the gas, definitely an external agent get involved, right? And when the gas expands, it can expand it by itself. So work done by gas, the expression we have discussed later in detail, right? So there are two things, and in the limelight of these two discussions, what we see, dq, again, let us remember the law, first law, right? First law of thermodynamics states that dq is equals to what? du plus dw, or that we can write down this as n cv dt plus p d. Okay, so this is the complete expression of the first law. Right. Graphical representations are also made for studying the variation in the thermodynamic state of a gaseous system. Right? This graph plot, okay, this graphical representation for studying the variation in the thermodynamic state. This graphical representation, when y-axis represents the pressure P, right, in Newton per meter square, and the horizontal axis, the x-axis, okay, is used to represent volume in cubic meter. Right. When a graph between these two thermodynamic variables, pressure and volume, is plotted, right, this such a diagram is known as indicator diagram. In the indicator diagram, and we have just seen, okay, that dW is equals to PD, work done by a gas is equals to PdV, right? A simple expression, or just work done is obtained by integrating these two. Okay. So if P and B is there, suppose there is a graph plotted, and you get a graph like this. You got a graph, okay, like this. A process taken from one state A to another state B, right? This is represented by an arrow. Arrow gives you the direction of the thermodynamic process. The process is taken from this A and B, the points represent thermodynamic states, and the arrow given on the graph gives you the flow, the direction of the process, right? Or how? Now check. Come on, let us say at A for this state, let the value of the thermodynamic variables are, say it is P1, and this is the pressure P1, right? And say this is the corresponding volume V1, right? And obviously there will be a temperature T1. And like in the second position B, final state, this is what? This is the called initial state. This is the initial state, right? And the second one is the final state. Okay, the gas is taken through this path from A to B like this, and at B, yes, there is a new set of value for thermodynamic variables. Means for here we can say pressure is P2, volume is V2, and temperature is say T2. Right? Here is the situation. So gas is taken from one state to another state, right? And that has been explained very beautifully in this graph. We can study everything about that. In such an indicator diagram, okay, the technique of getting the work done by the gas is then obtained by the area under the graph and the volume axis. So this shaded region gives you the work done by the gas in this particular thermodynamic process, which is A to B. This is AB, the curve. Okay, in any other case, say in one system, okay, say P and V is given, PV diagram is there. Okay, PV diagram is there, right? And a gas is taken from system A to B, right? When it is taken from A to B, right? What is the case? In that case, one can easily understand that the value of at state A and state B, right? The value of a thermodynamic variable, what? Pressure in this case, right? In this case, we can see even in these two states, right? The pressure, the value of this thermodynamic variable P is constant. That means pressure is P1 at A as well as B. Whereas the volume at A is V1 and the volume at B is V2. That simply means this gas is expanding. Why? As we can see from the graph, V2 is greater than V1. V2 is greater than V1. We can see the graph is expanding. Come on, find out the work done then. Work done by the gas, as I have told you, work done by the gas is the area between the curve and the volume axis, right? So this is what the shaded region, and the shaded region looks like in what? It is a rectangle. Okay, and in this case, the area of the will be, so work done by the gas in this case will be, work done by the gas will be, right? See, this is what? Length into breadth. Height is P1, right? And this is V2 minus V1. So this will be P1 into V2 minus V1. What a simple thing. So we can find out the work done in that case, right? Let us draw one more thing. Say this is P. The process is the thermodynamic process. Let me remind you, the thermodynamic processes in which, right? Okay, pressure is maintained, pressure is kept constant. Such processes are called isobaric processes. Such processes are known as isobaric processes. But here, if I can check it like this, in this way, okay, in this way, if the things are there, if a gas is taken from state A to state B, right? What is the case? Definitely in this situation, one can see that what? Volume, yes. Pressure is changing. Pressure in state A is P1, whereas pressure in state B is P2, but volume in both the states A and B is V1. That simply means what? There is no change in volume even during the change in state of the gas. So during the changing state of the gas, we can't see any change in the volume. That means the gas in the system is neither expanded nor compressed. Therefore, in that case, obviously work done will be zero. Work done by the gas will be zero. Okay? Keeping in mind these two exercises, the two examples, okay? And such process in which volume is kept constant is called isochoric. It's called isochoric. Okay. Let us see one more process. Okay. Let us see one more process. I'm drawing an integral diagram. P versus B. Okay. A gas is taken from A to B. It's taken from A to B, and it's taken from A to B. A to B. Okay, like this. Okay, fine. It is taken from A to B. It is taken from A to B. That means pressure corresponding to A, little bit P1, volume corresponding to B, maybe V1, temperature as usual maybe T1. Similarly, when it is at B, it reaches the B, right? It reaches the B. Definitely, what is the case? Right? We can see volume is V2, whereas pressure is okay. Temperature maybe say T1 here, temperature maybe T2 here, right? So in that scenario, what we can see, the gas is taken from A to B through the graph according to this path, according to the graph plotted, right? So this is the trajectory of the system, right? So this is the process, trajectory of the thermodynamic process in which the gas is taken, the system is taken from state A to state B, one state to another state. Right? And if it is now taken back from B to A, like this. Suppose it is taken from B to A like this. Yes. Definitely. That means this is a reversible process in which, right, or even cyclic also. So it is what starting from A going to be taken from A to B and finally from B to A. So it regains the initial value of its thermodynamic variables, or we can say what it returns back to its initial state after the completion of the operation or by the completion of the process, right? Such a process is known as cyclic process. Such processes are called cyclic process. It looks like a circle, right? Every parameter is regained or it comes back to here. Again and again things will be done. In such a cases, the work done will be. Now let us understand. I am using two kinds of steps, right? For first process means when it is A to B, right? A to B. You can see A to B, area under the curve and the volume axis, right? This is what the work done by the gas, right? In process A to B. Similarly, when it is taken from B to A, yes, there will be also work done. Okay, but since you can see what is happening in the second process, B to A, process 1 is from A to B, process 2 is from B to A. In the second process where we are moving from B to A, taking the gas from state B to state A, right? In the second way, we can see what? The gas is compressing. Definitely, the work done by the gas is negative. Whereas in the process 1, work done by the gas is positive. Work done by the gas in this process is positive, but the second gas is negative, and the total work done. And one we can see what? Positive work done. So work done in the process W1. One is W1. Similarly, work done in the process second is W2, and definitely is minus W2. Negative work done. So total work done by the gas. W total will be W1 minus W2. Since W1 is greater than, it is obviously visible, W1 is greater than W2, definitely the work done by the gas is taken, it can be clockwise. Okay, so in clockwise cyclic process, we obtain a positive work done. Okay. Here we will stop for a while. We'll have a short break and we'll be back soon.